Okay, I'd like to wrap up first order ODEs with some super fun application problems and see where all this sort of comes together in actual problems that I took from other books and other courses here at CMA. So I'm just going to jump right into this with a problem from reefers. So here's a problem. We're going to consider an insulated box with internal temperature U of T. Okay. So according to Newton's law of cooling, U satisfies the following ODE. It's du dt equals minus K times U minus T of T. And let me call this something here. I'll call this equation star, where cap T of T is the ambient temperature. Okay, so U of T is internal, cap T of T is the ambient outside temperature or external temperature. All right, so here's the problem. Suppose T, this function T, begins at 100 degrees centigrade and decreases linearly to 0 degrees centigrade in 10 minutes. Okay. And just for the sake of the problem, we're going to let K be 1/5, which is some kind of cooling factor. Okay. So part A, this by the way was an old quiz. Part A. We'll solve star. Okay. Notice that part of your solution goes to 0 as T goes to infinity. Okay, so this is called the transient part. Of the solution. And the remainder is called the steady state. Okay, and we're going to denote the steady state by S of T. All right, so we got some work to do here. We need to figure out a few things here. First of all, we're solving star, and so we need to get a handle on what cap T is. So what is cap T? A here. Well, it's linear, so it better have this form, right? Slope-intercept. And we need to find M and B. Well, it goes, so it starts at time 0, it's 100 degrees, and 10 minutes later it's at 0 degrees. So what's our slope? Our slope is 100 minus 0 over 0 minus 10, which is, what's that? Negative 10. And the y-intercept is sitting right there. So here's cap t. It is minus 10t plus 100. Okay. So let's rewrite what it is we're trying to solve here. We have du dt is minus k minus k times u. Where is it? Oh, there it is. U minus this t that we just found. I'm going to write it like this. Like that. Okay. And we know what k is, so this is now minus 1/5 u times 100 minus 10t. Being really careful with our negatives here. We have minus 1/5 u plus 20 minus 2t. Let me check that. This by that is negative. So the next one is a negative times a negative, so it's positive. And then we have negative, negative, negative. Okay, that looks good. All right, first thing to note, this is linear in u, the dependent variable. Okay, so let's rewrite. Into standard linear form. And what do we have? We have u prime plus 1/5 u equals 20 minus 2t. And there's our u prime plus pu equals g. Okay, so now we got standard form. And we're on our way to solving this problem. Okay, so let's find the integrating factor. It's going to be mu equals e to the p dt, which is e to the 1/5 dt, which is e to the t over 5. Okay, so there's our mu. Okay, let's be careful now. Now we write down, this is u e to the 5th, so that's u mu equals the integral dt. Okay, so now we have it in. So now we have some integrating to do here. So this is now equal to the integral of 20 e to the t over 5 dt minus 2 t e to the d over 5 dt. Okay, this first integral is not bad. When you flippity flop the 1/5, you get 100 e to the t over 5. We'll deal with the constant at the end. Okay, this guy takes an integration by parts. So let's see, you let u be t, dv is dt, du is dt, and v is 5e to the t over 5. Okay, so carrying on with our problem, being generous with our brackets. Remember how this goes. This goes uv, which is 5te to the t over 5 minus v du, which is 5, the integral of v du, which is 5 e to the t over 5 dt. Okay. All right, one more integration. So rewriting this, we have 100 e to the t over 5 minus 10t e to the t over 5 plus 50 e to the t over 5. And now we add the constant from all the integrals together on the right-hand side. And right, make sure my signs are right. I have minus 2 times minus 5 is 10, and 10 times 5 is 50. Okay. So let's go, so we can break this down a little bit. Oops. Let's rewrite this. Combine like terms. So this is 150 e to the t over 5 minus 10t e to the t over 5 plus c. C is very important in differential equations. Okay, so now we solve for u by multiplying through by e to the minus t over 5. So we have 150 minus 10t plus c e to the minus t over 5. And that is our general solution. Okay. So have we done all of part A? Let's check here. Let's check here. Part A said solve star. Okay, we solved. Notice that part of the solution goes to 0. That's the transient, and the remainder is called S of t. All right, so let's do that. Hopefully it's pretty clear because of the exponential. As t goes to infinity, this piece goes to 0. So this is the transient part. And it goes pretty fast because it's exponential. So that means that this piece is we're going to call ST. This is the steady state. Okay, so let me make sure we did all of part A. That's part A. Okay. Part B. Sketch the graphs of S of t and t of t on the same set of axes. So we're going to make sure we set this up right. So here's the time, and this will be y. So we're going to go what? So I'm going to go 50, 100, 150. All of this takes place over 10 minutes. So 1, 2, 3, 4, 8, 9, like that. Okay, so cap t went from, put it in blue here, started at 0. Sorry, it started at 100 and went to 0 after 10 minutes. Well, let's look at S of t. S of t, which I guess I'm going to put in red here, started at 150. And after 10 minutes, it went to 50. Okay, so this is S of t, and this is cap t of t. S of t is part of the internal temperature. So, and they both have the same slope, right? So m is -10, m is -10, so they're parallel. And now for my favorite question. see. Does the graph make sense? Well, you've got a box sitting here that's being chilled by the outside temperature, which is linear. So eventually the inside, the steady state, is also going to be linear. Just imagine as the temperature goes down in your car, or outside of your car, if you leave it alone, so does the inside, and it goes equally after a bit, after the transient part drops out. So the answer, yes. Okay, here was an extra credit piece. So guess what U of t looks like. All right, just sketch it as you might think it's gonna appear. Well, let me write down U here. It's this 150 minus 10t plus c e to the t over 5. So at the beginning, it's going to be pretty high, but this guy goes to 0, so eventually it's going to be asymptotic to s, right? Because this guy goes to 0 and all that's left is this piece. So my guess is it's going to come down like this and just level out along the asymptote there. Something like that. It's just for fun, trying to think about what's going on. So let's have a look. Let's have a look. Graphing calculator. So here is 100 minus 10x. This is that's y. And let's do this. 0, x, 10. What happened? See if I can't. Anyways, there it is. And then we have y is now 150 minus 10x, 0 less than x less than 10, which is exactly what we had. If I could get this axes to line up right. Okay, and let's put in u now. So u is 150 minus 10x plus e raised to the minus x over 5. 0 less than x less than 10. How do I get this axis to behave? I used to be really good at this. It's been a while. But you can see that the green function, which is the one with the transient piece there, lies right on top of the blue one, which is s sub t, so it makes sense. Okay, so that was fun. And it was a good application of first order ODEs. This comes from circuits, which I know a lot of you are in right now. Several years ago, a group of students who were in circuits in this course, exactly like some of you are now, brought me their notes and said, we think we're doing exactly what we're doing in class in circuits. So they gave me their notes, and I unraveled it from Mike Holden's class. He's one of my favorite people at CMA. And this is what I came up with. And it was really fun to sit in class. Well, I'm going to show you now. So from circuits, this is straight out of circuit notes, RC circuits. Right, so we're looking at RC circuits. Later on in the course, we look at, what is it, LRCs or LRDs. This is an ODE, first order. And it's linear in V sub C. Okay, so let's solve it and then see what you do to solve it in circuits. So for us to solve it, we need to put it in standard form. So I guess we have to assume, first of all, assume RC is non-zero. Otherwise, this makes no sense. So in divide by RC, you get dVC dt plus 1 over RC VC equals 1 over RC VS. All right, now we have it in standard form. Find the integrating factor. This is cool. So mu equals E to the 1 over RC dt. Are we using t's? Yep. Which is E to the t over RC. Okay, so there's our integrating factor. So now we write down the solution just like we did a minute ago. So it's VC E to the t over RC equals E to the t RC times the right-hand side, which is 1 over RC VS. And we're integrating this with respect to t. Okay, so move the constant out front, which is VS over RC. We have E to the t over RC dt. Okay. Do a little U sub and integrate, and you have VS times RC. Then you have an RC here, E to the t over RC plus a constant, right? And I won't use C as a constant because we're already using it. I'll use D. All right, just a constant. Okay, so rewriting, we have VCE to the T over RC equals VSE to the T over RC plus our constant. Okay. So now multiply through by e to the minus t over RC. So we have this. VS plus VSD e to the minus t over RC. Okay. And that's our solution. All right, and that's from our class. You all could do this by now. And sure enough, as t goes to infinity, because it's in the exponent of the e, VC approaches VS. Okay, so these are from Holden's notes. Notes say plug in y equals k1 plus k2 e to the st. All right, now this is where you got to start looking. Okay, you got this and this, this and this, this and this. Okay. So this is from the notes. This is from the circuits notes. Just plug this in. Okay. Then it says let let K1 equal Vs. Okay. Well, that makes sense. It's exactly what it should be. And it says let S equal minus 1 over RC. Okay, so this S here is what? It's minus 1 over RC. So that makes sense too. So this is all good. So this is how you learned it in circuits. And this is exactly what we found. I don't see in the notes anywhere where it says let K2 be VSD, but it doesn't matter. That's not important. Why? Because that term goes to 0 pretty quick, depending on how big R and C are, right? And so, yeah, there's another application that you're doing in one of your courses right now that is exactly what we've been doing all along. So, all right, one more. Here's an equation. It's called, I've never heard this name before. I know its real name, the other name, but what is this called? The Verhulst. The Verhulst equation. He was a Belgian mathematician. Belgian dude. I study population growth, which I'm fascinated by. And he came up with this equation. It looks like this. It's dy dt equals r. Well, let me do it the long way. R minus ay y. Okay. And this is also now called the logistic equation. If you look at this for 1 second, you'll see that it's Bernoulli. But your book doesn't see that. And it goes through a really complicated, I did it and it's super cool, but it's you have to do partial fraction decompositions and all this other stuff. But if you do some moving around of things and define a new term, this K I'm about to show you, which comes from so we have y prime equals r 1 minus y over k y, and r is this intrinsic growth rate. That means the rate of growth that you would have with no outside factors, nothing holding you back, no famine, no bad weather, no anything. Okay. And there's a way to interpret k as well. So this is just another way of I mean, basically all we have is k equals r over a in this guy here. All right, so to solve this, the book used the separated variables, and then used partial fraction decomposition. How many of you remember that from Calc 2? I did it and it was a mess. But I think the better way is to look at this as Bernoulli, right? So now we have y prime equals ry minus ry squared over k, right? And then rewriting it, we have minus r over k y squared, and this is Bernoulli with n equals 2. And it's a really clean solution. In fact, you did it for homework. So there you go. I'm going to assign a couple of these for homework, just so you have a feel of how to interpret these, and hopefully you enjoy it.